All right, this is Physics 1C for December 1st. On the top, you can see what we're going to discuss tonight. We're going to talk about radiation pressure as well as getting into some vector calculus stuff, talk about the curl and divergence of vector fields. We're going to use the ideas that we developed there to take what we know as Maxwell's equations and turn them into a different form. It's called the differential form. This is usually the form that you'd see on a t-shirt or like in the Physics 1C classroom at the school, kind of sitting up on the top of the board. All right, so we have one thing to talk about from last time, though, and that's radiation pressure. Just as a reminder of what we did last time, we talked about something that's called the Poynting vector. The Poynting vector, we used the symbol S to represent it, and it was given by this expression. You take basically the electric field, cross with the magnetic field, and divide by mu naught. And the Poynting vector is something that describes basically the kind of intensity of, the energy that's transported by an electromagnetic radiation. So it's like the intensity of, you would just say light, I guess is the simplest thing to say, or as we've described it, as electromagnetic radiation. And since it's intensity, by intensity what we mean usually is basically power per unit area that's delivered. So it's related to kind of the rate. So power is the rate at which energy is flowing, and you divide that by the area. And what we'd like to do is we'd like to connect this to, if we know that light waves transport energy and therefore transport power, we'd like to understand, can they also possibly transport like a force, like a type of pressure? And I think the easiest way to think about this, there's other ways to get to the same result, is just to remember something from Physics 1A, which is that you can get power from a force and a velocity. So for example, if you have a car that's traveling along a road with a constant speed, you can describe the power output of that engine by figuring out the size of the drag force acting on the car, and then figuring out the force that the engine needs to maintain to kind of overcome the loss through that. And it ends up being related to the velocity, because the idea is the faster that you travel in a car, the more force that the engine needs to provide to keep it moving at that velocity. Obviously, the engine needs a force to increase velocity, but once you're moving at a certain velocity, you have inertia. And so with that inertia, you can figure out how much power output the car has, right? And that's done by taking the force that you travel. I'll write it out actually so that we're really clear. And you multiply by the velocity of the car, basically. So if we want to figure out something about pressure, this helps, because contained within this is force divided by area, right? So this is kind of how the argument goes. The Poynting vector is S, that is to say the intensity of the light, is equal to power over area, which is equal to force times velocity over area. And we know that the velocity of... Yeah, that's exactly right. Mr. Miori says, well, we divide the Poynting vector by the speed of light. That's right, because right here we have velocity, and for light, we know that it's traveling at a certain speed, which is called c, the fastest, as far as we know, the kind of fastest attainable velocity that exists, kind of the speed limit to the universe, the speed of light. That's your velocity. Then what you can do is say that, let's just write this more in symbols like we normally do. We'd say S is equal to force times the speed of light divided by the area. We take the speed of light and we divide it to the left-hand side, so we get S over C is going to be equal to force over area, but force divided by area is pressure. So we're going to call that radiation pressure. So if we take S over C here, we're going to call, in this case, we're going to call it radiation pressure. And we'll use the symbol P with a little sub RAD for that. So S over C then, from this, is going to be equal to radiation pressure. And we had said that S was equal to E cross B over mu naught, so in terms of the magnitude of S, it would just be E times B divided by mu naught, and now we just multiply by C. And this gives us the radiation pressure. Or just S over C. This one also works. It's actually a lot simpler just to take the Poynting vector, if you already know it, and then divide by the speed of light. Let me just clear this up a little bit. Like And so that's what we call radiation pressure. It's a type of pressure, and so it can deliver momentum in the same way that, if you have a gas balloon that's like filled with helium and you blow on it, it can move due to the pressure that the blowing on the balloon creates. You can also say that this type of pressure can deliver momentum as well. So this is a kind of, we call it radiation pressure, but there's kind of another name for it, which would be light pressure. It's literally the pressure of sunlight. So sunlight, when it hits the ground, it puts pressure on the ground, and if you have stars, they push a lot. The sun's a star. They push on their surroundings with this type of light pressure. And I like this picture here from your book that describes this is a interstellar gas cloud. It's a group of intensely luminous stars that exert tremendous radiation pressure on their surroundings, aided by a wind of particles emanating from the stars. These are two separate phenomena here. One is the light pressure, and one is a particle wind. And it says, over the past billion years, the radiation pressure has carved out a bubble within the cloud 70 light. That's just an incredible number. 70 light years across. So I guess from edge to edge here or something, wherever the biggest one is, 70 light years, which is just insane. But yeah, so what they're claiming here, at least, if we can believe them, is that the spread of these gases is due to radiation pressure. The light from the stars in the middle pushing on this gas and spreading it all out like this. That's an incredible force. The pressure, as we will see, can be very small or it can be very large when you multiply it over thousands and thousands of stars, I guess. Okay. Anyone have any questions? To be clear, there's kind of a range of ways in which this can happen. So you can kind of have a situation like the following, where if you have a reflective surface, like a solar panel or a mirror or something like that, and you have a light wave and it comes in and it bounces off, it's going to deliver pressure on the surface here. Like if the surface, we call it A or something like this, it's going to feel a force that's going to push it this way. But the thing is, if it's reflective, what's going to happen is you're going to get double the size of this over here. So the radiation pressure really, in this situation, is going to be 2 times the, and usually here what we end up using is the average Poynting vector, because this is often what's much easier to measure. Like we know kind of the average Poynting vector from the sun. We might not know what the instantaneous or max. We can calculate the maximum value, but and then you just divide this by c. That's for the full reflection case. And then the other possibility would be if you have a darker surface, like if you have a black matte surface, something that absorbs. So you can have full absorption. And with full absorption, what would happen is that the light would come in and it would be fully absorbed by the surface. In this case, your radiation pressure, you're going to take just S average divided by C. And if you have something in between the two of them, then you're going to get kind of a fraction in terms of how much light actually goes through. So if you have like 50% reflection, this could become like 1.5. Sorry. Yeah. I think that I don't think your book puts it this way, but I think other books would say, or if you take 1 plus the fraction and you multiply by S average over C, this gives you your radiation pressure, where F is kind of the fraction. Like if it's 50%, you'd be 1 plus 0.5. If it's absorption, this one would have F equal to 0, and reflective would have F equal to 1. This would be like 100%, right? So if it was like 70% reflective, you put 1 plus 0.7. And the idea, of course, is that when something bounces off of a surface, it imparts more pressure, because that's just how it works. If a ball bounces off of a surface, instead of a ball kind of being absorbed by a surface, and just kind of like falling flat, then the ball that bounces is going to deliver bigger force. This is another 1A thing. Do you guys remember this? If I have a surf, there's this demo we do in Physics 1A where you bounce a ball. It's called a happy ball, and the happy ball basically bounces down, and then it bounces back up to really close to the same height. And then you have a sad ball, and the sad ball, what happens? It's kind of like a piece of putty. It just falls down here, and then it goes splat on the ground. It doesn't bounce at all. And the question we always ask the students is, which one delivers a bigger force? Do y'all remember this one? I'm sure someone has to remember it. So the way that, I mean, if you took 1A last semester, you probably didn't see a demo because we were probably already in lockdown or whatever. But I guess you can think about it for yourself if you want to, because it's directly related to this, and I think it's always good to kind of go back on things you've learned before. What does your intuition tell you? Which one of these would deliver a bigger force? Would it be the ball that bounces directly off the surface, like a normal bouncy ball, and comes back up really high? Or would it be like a beanbag that you drop and it hits the ground like this? And assume kind of they're the same size, same mass. Which one delivers a bigger impact force to the floor? Yeah, the bouncing one does. Yeah, exactly. Because its change in momentum is twice as big, right? The change in momentum goes from downwards to upwards, which is from positive to negative, so to speak, right? Yeah, momentum, exactly. And so that's what's happening here with the light, is the light is actually delivering momentum to this object, because a change in force is a momentum, or a change in momentum implies a force, and yeah. So this is pretty groundbreaking. The idea that light itself can exert pressure, I think, kind of also goes against your intuition in a way. Right? I mean, I don't think you naturally think that light should exert a pressure because we don't feel it. We don't feel pressure on our bodies in a room that's lit compared to not feeling pressure in a room that's dark, right? You might feel the pressure of the atmosphere. That has an effect, and part of this is because the force here is quite small, as we'll show in this problem that we do. But when you add it up over enough stars, it can really add up. Also, I mean, aided by the wind of particles. The sun is streaming out something that's called the solar wind of charged particles that go throughout our solar system, that they actually have the effect of sweeping the solar system clean, which is kind of cool. They sweep the solar system of gas particles and dust particles and stuff like that. But yeah, to give you an idea of like just how small this would be. So this like sunlight. From our sun has a pointing vector, which is this I mean, the pointing vector is such a weird way to say this. The intensity of sunlight, way easier to say that. The intensity of sunlight is about 1,400 watts per meter squared. That's the unit we use for it, is power divided by area, right? And so if you want to figure out the radiation pressure associated with the sun's light, right, then, well, this says that all you really need to do is to just basically divide by C. So if we just look at the base definition here, if we just take S over C, then we would take 1,400 watts per meter squared, and then this is the problem. You have to divide by the speed of light, and the speed of light is 3 times 10 to the 8 meters per second. So if you divide those, you're obviously going to get a really tiny number, right? This is 1.4 times 10 to the 3, so it's basically like 1.5. 1.5 over 3 is like a half, and then you're multiplying by 10 to the minus 5. So it ends up giving you something like this, about 4.7 times 10 to the negative 6 newtons per meter squared, which the symbol we use for that is pascals. But I'm going to write it as newtons per meter squared because with the pressure over here and stuff, this is we also call this a pascal, in case you didn't know. So this would be kind of the pressure of sunlight. This is well compared to something that maybe is more closer to our understanding. Just to give you an idea of how small this is, atmospheric pressure is about 1 times 10 to the 5 pascals, right? So you're talking about 11 orders of magnitude, which means that this is negligible, at least on Earth's surface, because there's so much other pressure that we have to think about, right? But in outer space, where there is no other real pressure, this can be sizable. And actually, one of the kind of biggest ideas about radiation pressure in modern astronomy is that you could use this idea to kind of like ride on the pressure of the sun's rays in the same way that we ride on the winds of the ocean, you know. And the thing that they use to do this is called, like Mr. Meowers is saying in the chat, it's called solar sails, and they are these very, very, very large pieces of metal. So they're reflective, because reflective gives us the, double the pressure. They're these very, very, very thin, gigantic, kind of collapsible. They've got these like long arms, and they're basically just made of a very light material. It needs to be really light because the pressure is super small. So they need to be huge, because part of what you can do here with this pressure is if the area is big enough, right, the force is going to be equal to the pressure times the area. So if you get an area that's on the order of 1,000,000 meters squared, you're talking about like about half a Newton of force or so. 5 newtons of force. Think about that, 5 whole newtons. But if the mass is low, then you get force, right? And it doesn't require the input of a fuel. And that's kind of huge, right? Because one of the, well, maybe this isn't obvious, but one of the biggest problems about traveling in space is the payload has to be extremely small relative to the fuel that you carry with it if you want to go anywhere, let's say outside of our solar system. So solar sails provide an opportunity to possibly accelerate a vessel, and this vessel couldn't carry much. It'd probably just have some sensors on it, some cameras, these kinds of things, as well as a radio to send information back. But, as long as we can get it up into space, it can do the rest. And so, when we launch people off into space, the ratio of their fuel to mass rate, like the fuel to payload ratio, it's like 15 or something like that. You have like 15 times as much mass and fuel that you carry just to get into orbit, basically, compared to the payload. So that's why these rockets are so big when you see them launch off. It's all fuel, and they basically just dump the canisters as they go up, until very recently when SpaceX started recycling their canisters and stuff like that. So solar sails is a pretty good idea. You can move around space without the need for a fuel source, just like you can move around the ocean. And just as people moved around the ocean in the age of discovery or whatever, when people were moving all across the planet and people circumnavigating the globe, and they were able to do this because they could ride on the wind of the Earth, and this is like riding on the wind of the solar system. So anyway, there you go. All right, anyone have any questions? New institution. All right, so this is a picture of just solar panels, because part of the idea of the pointing vector is that we could absorb the energy with solar panels. But let's do just a quick problem here, and then we're going to go into doing some kind of vector calculus stuff and talk about Maxwell's equations. Make this a little bit smaller here. Okay. So power and pressure from sunlight. An Earth-orbiting satellite has a solar energy collecting panel with a total area of 4 meters squared. If the sun's radiation is perpendicular to the panels and is completely absorbed, find the average solar power absorbed and the average radiation pressure force. All right. So you have panels. They're feeling the sun's light come down directly perpendicular to them. And we're going to use the value for just look at my notes here, I'm pretty sure, we're going to use the same value for S average that we did in the previous problem. So the one where it's about 1,400 kilowatts, no, not kilowatts, sorry. 1,400 watts per meter squared. And it's a pretty easy problem here. So it's an area of 4 meters squared. And all we want to do is just to find the average solar power absorbed. So for power, we can take S average, which is basically intensity, which is power per unit area, and multiply by the area. So 1400 watts per meter squared times 4 meters squared. 4 meters is a pretty big solar panel. That'd be huge. Times 4 meters squared. I don't know, what is that? 28 times 2, 5600? 5.6 kilowatts, maybe? That would be the power. That's a decent amount of power. 5.6 kilowatts. You could use that to run like an air conditioning unit and maybe a dryer and watch TV. That's a decent amount of power, actually. It's a lot of power and energy that comes from the sun. Of course, the idea that the sun's radiation is perpendicular is pretty important to this, because the actual percentage of energy that you can actually... Yeah, it's not 100% efficient, exactly. Oh, yeah, definitely not. You'd also have to... So this is the power absorbed. It doesn't tell you the amount of electricity produced. Then the electricity produced is usually something on the order of about 25% of this. And that is like fundamental to the cells themselves. We're still improving like solar cells. There's a lot of research being done on this, but I think the really good ones are between 25 and 35% efficient or something like that at converting the solar power into electricity. And then the sun's not up all the time. In California, it's up every day, but it's not up at nighttime. And the energy that's transported is only at a maximum when the sun's light comes straight down, because it's a kind of flux, right? So you take the direction of the sun's rays, and it has to be completely perpendicular to get the maximum. So, but nonetheless, if you can store the energy and you get enough of these panels, you can still use it. And that's definitely, hopefully, the direction that our world's going, is to using more and more solar power, because it seems like the easiest type of power to rely on, and it's kind of abundant in the sense that some of you have to know this. How long is the sun going to keep burning, or is it going to burn out soon? Anyone know? Is it going to burn out anytime soon? I can't remember if it's 5 billion or if it's 5 million, but it almost doesn't matter, you know? It's a lot. It's a lot. 4 billion, that sounds right to me. I think in it's like 4 to 6 billion years, they estimate, our sun will go supernova, and what will be left was it'll be a red dwarf at that point. It's going to kind of swell up and be huge, and it's going to be, the sun's orbit's going to engulf like the inner planets and stuff like that. We won't be around. None of us will be around. It will be more likely that we destroy the planet before that happens. But the point of me mentioning this is that sunlight's going to be there forever. So as long as we can keep the Earth here forever, we're good, right? Humans will have made themselves extinct by then. You think so, Adele? Probably. Maybe something like that. Maybe robots will be moving around on the Earth or traveling between stars. Who knows? All right. The second part of this is to find the average radiation pressure force. So to get the force, you take pressure times area, right? And the pressure was S over C. So you take S average divided by C. It says that it's completely absorbed. So you take S average over C, that's the radiation pressure, and we multiply by the area. So I guess it's going to be what we just did, divided by C, right? So we can just take 5.6 or 5,5600 watts and then divide by C. And of course, this is going to be a really tiny amount of force, right? 1.9 times 10 to the minus 5. Very, very tiny amount of force. These things, by the way, I guess I should be more clear about this. This idea of using this force to do stuff, we've done it before. Like, solar sails are something we've actually produced. We've put things up into space, and we've shown that you can manipulate the orbit of the vessel, and just by using the solar sail. So it's not something of science fiction. This is something we've actually done before, and we're still in the interest of kind of continuing along that path because it seems really fruitful, especially as a way to kind of get some early probes out, because we don't really have a good enough fuel source currently to realistically get to these distant star systems, because The closest star system other than the sun is like 3 to 4 light years away. It kind of varies, but it's really far. 3 years even traveling at the speed of light. But anyway, so that is kind of the end of what the book talks about on electricity and magnetism. And so what we're going to do now is we're going to go a little bit deeper because I think it makes sense to kind of at least finish this this course up by using some things that some of you may have seen, some of you may haven't, from your vector calculus class. These things called the curl and divergence. If you haven't, I'll do my best to describe what they are. As long as you understand a little bit about calculus, you should probably be able to follow all this stuff without a problem. And really the goal is to just get to a different version of Maxwell's equations that can be useful in certain situations, and I'll give one particular example of a way in which it can be useful. So I don't know how long this will all take. It might not take all of the rest of class, but I want to give you guys time to finish up your homework and stuff. So if we do finish early, then we finish early, but if we don't, then if you find this even remotely interesting, and some of you might not, that's fine. But if you find it even remotely interesting, you probably have a lot of questions. All right, so I had to do this for class because I think this would take too long for me to do in class. So I kind of did this thing here. We're not going to do this problem. This problem's not very interesting. You can look it up in the textbook if you want to. All right, so, oops. How far up am I going? I'm going to here. Okay, I guess we can start right here. And really, I don't need this yet because I need to just describe what these things are. All right, let's just talk about what curl, gradient, divergence are. Those things y'all have heard of before? Curl, gradient, divergence? I think we've talked about gradient at the very least in this class, right? All right, so I think we got to say what they are in advance, just because last week in your calculus class. Okay, this is good timing then. All right, so first of all, we need to define something called, well, you all tell me what you call this thing. I think I've heard a lot of names for it. Okay, gradient is not a good word for it, unfortunately. There's a gradient operation that involves this. I've heard nabla, definitely. I've heard del operator. Del, you've heard that too? Upside down delta is fine too, however you want to describe it. It's definitely an upside down delta for sure. All right, so this is an operator, okay, and it has this form. You take partial with respect to x, I hat. You're not taking the derivative of I hat, because I hat is just a unit. It doesn't have any. I could put this in front of or behind it. It doesn't matter. And then plus del y j hat. And then plus del y, del z k hat. Where I, j, and k are your normal unit vectors that point along the x, y, and z directions, respectively. With this thing, we can define an operator that's called, we can define an operation. So this itself is called an operator because it needs to act on a vector field to do anything or a scalar field to do anything. So the first one that we can talk about is the gradient. This is one we're not going to talk about much today. The gradient is the operation you get when you take nabla. Now notice it's a vector, right? And if I want to multiply a vector times another vector, then I need to do some things. I got to do either a dot product or cross product, right? So the only thing that we can use for the gradient that doesn't involve a dot or a cross would be to multiply it by a scalar field. So I'm going to use a scalar field that we already know about, which is the potential, the electric potential. That's a scalar field, right? We've called it V in this class. It's commonly called phi in a lot of other literature. Regardless, what this would look like would be del V, del x, I hat, plus del V, del y, j hat, plus del V, del z, k hat. And it turns out that this, if you look at the units of it, has the exact same units as the electric field. V is potential, electric potential, or voltage. Voltage divided by distance is like volts per meter, volts per meter, volts per meter. So this has the same units as the electric field. And we have a relationship that we derived earlier in this class, which is that if we take the negative of the gradient, This gives us, does anyone remember what this gives you? It starts with an E. This gives you the electric field. So if you know the electric potential is a function of x, y, and z, you can find the electric field. I'm pretty sure we did an example of this in this class, but I may be wrong. I'm not sure if we actually got to it, but I think we did an example of how you can prove that, for example, any of the electric potentials that we've gotten in this class can be turned into an electric field. So this is an operation that takes V, which is a scalar field, and by taking the gradient of it, you get a vector field, okay? Now, the word gradient is a really good word to describe what this thing actually does, because another example of how you could describe the gradient would be, imagine that you have like a mountain, and you want to describe how slopey the mountain is, okay? Now, we know in mathematics how to describe the slope of a curve in 2 dimensions, right? X and Y. If you have a curve, you can take the derivative of that curve, and it tells you the slope in the xy plane, right? The gradient describes how you would do that over like a 3-dimensional surface, though. So if you have like a mountain, then the gradient would describe how slopey the mountain is at every single point on the mountain surface, basically. So that's the gradient. Okay, now that's an operation that involves taking the nabla operator and just multiplying it by a scalar field, right? This is a scalar. V is a scalar. The other thing that we could do, though, is we know other operations that involve taking a vector. This is a vector again. And the next one is called divergence. And this is either written as like, you either put the letters div, or I think the better way to do it is this, because it kind of tells you everything you need to do. The divergence is gotten by taking the dot product between nabla and your vector field, and since the electric field that we've learned about in this class is an example of a vector field, it's just as perfect one that we can actually use to actually do divergence of, and it actually has some physical meaning that we'll get to today. So if we take the divergence of the electric fields, the way that this ends up being written, I don't know if you want me to write this all out. I guess we'll write this one out, because we're not going to do the next one because it's way too long. But divergence, right? So we copy. I'll copy paste. This will save a little bit of time. We'll just change the color. If we take this and we do a dot product with the electric field. So how will we write the electric field? So we can write any vector in general, depending on what coordinate system we want to write, like this. Cartesian coordinates probably the easiest, and the ones that we're all probably the most familiar with. So I can write the electric field in component format like this. By the way, the nabla operator has a version of this in spherical and cylindrical coordinates too. So this is the operator in XYZ or Cartesian coordinates. You can also write it in other coordinates. Either way. And then all these other operations work that way too. So what you get now is when we take the dot product here, you look at each term, and if we go term by term, if like, for example, we look at these two terms right here, what we get is del EX del X. So we have right? And then I dot I. And I hat dot I hat, what's that equal to? It's 1, right? Yeah. So we don't really even need to write it. So since it's I hat dot I hat, we'll just leave it. We don't even really need to write it, right? But when we do another term, for example, like if we do this term dot product with this term, in that one we're going to get an I hat dot J hat. But then because these two are perpendicular to each other, the angle between them is 90 degrees. So it's 0, exactly. So really, the only terms that are not going to be 0 are the ones that have the same letters, right? So it'll be like these two, and then like these two. Those are the only ones that are not going to be 0. So this one's the easiest one, divergence. For one thing, the answer is a scalar. That's kind of handy. Scalars are always really easy to deal with. So what we're going to get is del EY del Y. from the second two. And then we'll get del EZ, del Z. And this is what we call is the divergence. That's the wrong way to draw that. This is the divergence of a vector field. Right there. And what is divergence? Well, I'm going to prove to you that this is kind of like flux per unit volume. Flux per unit volume. We'll prove this as we get into this, but just for now, think of divergence as the flux per unit volume. It's a kind of way of describing how much a vector field is either flowing out or in of a point. And so you could think of something like a sprinkler that has water spraying in a bunch of different directions as having a type of positive divergence, whereas a sink has a type of negative divergence, if that makes any sense. So a sprinkler, let's draw a sprinkler. Let's say I have a sprinkler and it's just spreading water out in all kinds of directions as kind of like a positive electric charge would do for an electric field. We'd say this is a system where if I was to like put a little box around it, I would say this would be positive divergence. And same thing would be true for like the divergence of a positive point charge, if you put a box around that. And then the other option would be I could have like a sink. A sink would have like water flowing into the sink. And this would be negative divergence. So that's negative divergence. And if you have equal amounts flowing out and in, you get zero divergence. You can kind of see why it's related to flux, maybe, if you understand flux pretty well. All right, any questions about divergence? And then the last one, it's called curl. And this is found by taking we'll use a different symbol for this one. This one is done for, this one describes kind of like circulation around kind of a circulation of the vector field, we'll say. And the way this one is written is by taking a cross product. So again, we'll copy paste here. I'm not going to write out every term of these, but maybe we'll do one of them maybe. We'll copy this one. In both cases, we'll make them the same color. And then we'll get rid of this and this one, and we'll put a B in there. Probably could just turn those into B's, but wouldn't look very good. Bx, by, bz, and then we need to take the curl of this. So that means we're going to do a cross product. If you put a twig in water, what direction does it rotate? That's how I recall it being described. Yeah, exactly. I like to think of a paddle wheel, but it's exactly the same thing. So curl is given by this. Now, if we want to do this one, there's going to be a total of 6 terms that are not 0. That's a lot of terms. I believe the one that we're going to derive is going to be the k-hat term. So let's just use that one as an example. To get k-hat, there's 2 different ways you can do it. K-hat is equal to I cross j, or k-hat is also equal to negative j cross I. So there's going to be a component of this that looks something like this. If we look at the I cross j term, that's going to be this term. Maybe I just underline it. I cross j is this one and this one, right? So it's del by del x. And then it's going to be minus, and I already know what this is, so I'm going to write it, and then I'll go back and show you where it came from. But you basically just replace the x and the y's here. The other one comes from negative j cross I hat. Well, we have a j cross I hat right here. So underload those. This is j hat cross I hat right here. And that's del bx del y, right? Del y bx. So that's what shows up over here. But then you need a minus sign because the j cross I gives you a negative k hat. I don't know what the easier way to understand this is. It may be a little easier if I write it like this. Doesn't matter which side we put the negative on, but either way, that's what you're going to get. And, I mean, we can write out the rest of these, I guess. I don't know how much you guys really want to see them, but the j-hat one, they're all going to have the same form. It's going to be del b. The thing on the bottom is going to be like it's either going to be a z or an x. It's not going to be a y. And to get j-hat, see, I have to go through and like write all these down too. This is the only problem. To get j-hat, you want to do k-hat cross i-hat. So I'm pretty sure this is going to be del z in the bottom. We're going to have x in the top minus del bz del x in the bottom. I think that's what it's going to be. And we can check. So k-hat cross i-hat would be this one and then this one. So that's del z bx, right? And then the other one, you just flip it. And then the final one would be plus i-hat times... To get i-hat, we're going to have to go j cross k. So the j is here, the k is here, and then you flip them. Let me look at this and make sure that actually works. Y to z, right? Yeah. So that whole long, nasty thing is the curl. The curl's kind of the trickiest one or whatever. There's the curl. It has symmetry to it. I don't know if it's beautiful, but it's got symmetry to it. And you could figure it out as long as you know the operations and these other things, which those can all be memorized. All the tricks to get it can be memorized. You don't have to memorize the whole thing, right? Okay, so again, the idea for the curl is kind of like you look at your vector fields and you put a little paddle wheel into your vector fields and you determine if the vector field turns it, basically. You said if you put it... Why'd we do this with B and not E? No reason at all. This B could have been a Z or a K, or it doesn't matter. This was just a vector field. E and B are just any vector field. These are just mathematical operations so far. We will talk about divergence of E, divergence of B, so divergence of the electric and magnetic fields. We'll discuss those, and we'll discuss the curl of the electric field and the curl of the magnetic field, because all four of them matter. All four of them matter in describing Maxwell's equations. Okay, I think we've got everything we want there. So maybe we actually go into the first derivation and see if we can knock that one out before our first break. Any questions so far? Oh, let me just give you an example. I gave you an example of positive and negative divergence, okay? But let's say that you have a uniform vector field, okay? So I have a vector field in which all of the electric field lines, let's say, are going in the same direction. And instead of talking about electric field lines, water flow definitely does help. So if we imagine that we have a stream and it's flowing continuously like this, and then we take a little paddle wheel into our stream right here, right? And we want to kind of test how curly it is. The idea would be that this paddle wheel that we place into our fluid would have equal forces on the top and equal forces on the bottom, which would tend to cancel out, and so it wouldn't flow. In order to actually make our water wheel flow, we'd have to take the paddle wheel and get it out of the field so only one side was in. This is what you do with any water wheel, right? You have it so only one side's being hit. If it gets hit by both sides, all right, then you're going to get zero curl to your field. However, if your field is not uniform, meaning if there is bigger field lines on top than there are on bottom, so let's say you have a vector field like this. This is, again, very, very simple. This vector field, you could imagine that if I put a paddle wheel in here, if it's stronger on top than it is on bottom, then it's going to have a curl that goes this way. And I think that you call this negative curl. You'll have to remind me what convention you use in mathematics, but I think if it curls to the right, clockwise, you'd call it negative curl. And if it curls to the left, you'd call it positive curl. I think that's the notation. Actually, I'm virtually certain of that because it has to be related to the right-hand rule. It has to be related to the right-hand rule at the end of the day. So a curling of this way would point into the board, and a curling to the dex is positive? What's dex mean? Dex is positive and lev is negative? What is dex and lev? What does that mean? Dextroratory. Oh, come on. What does that mean? Never heard that before. Dextroratory. Sorry, I'm just... It's a physics word? All right. So I'll just go ahead and say that it's... Positive comes from when it's a physics word. Okay, it's not a word I'm familiar with. Ash, sorry. Maybe it comes from a field that I'm just not... that I haven't studied. Dextrorotary. All right, we're gonna look this up. I'm assuming you didn't make it up, but I just want to see what it means. I'm gonna assume one of these means clockwise only is counterclockwise, but I can't be sure. Let's see. Rotating in a plane of polarized light ray to the right. Okay, well now you're thinking about, this is like almost like helicity. This is only for light, it says. Oh, nope, but then it specifically says that it's clockwise or counterclockwise. Okay. All right, well, whatever. So it is counterclockwise and it's the same thing. It's counterclockwise and clockwise. So anyway, so clockwise is going to be negative, right? Okay, we're not going to worry about that because it's just a convention regardless. All right, so definitely follows by the right-hand rule, though, from what I'm reading here. All right, so yeah, let's get into how we can connect these things to flux and how we can connect curl to kind of the circulation of the line integral. The way I think of curl, so if divergence of E is flux per unit volume, then this one is going to be, curl is going to be circulation per unit area. Kind of circulation like around a perimeter, actually. But it's circulation per unit area. So flux per volume and circulation per area. No, it's not a distraction. I just never heard of them before. I was just kind of surprised. It's always good to learn new things. All right, so we're going to use this. We're going to have to reference back to these things, but we'll just leave them up here as a reference because what we're going to prove when we do this is that each of the pieces of what we need is going to come out of kind of a more geometric way to understand this. Let's just zoom out on this, I think. Okay, so what we have here is... Okay, so what I've drawn here is like an XYZ coordinate plane with a cube on top of it. And this is going to be the kind of normal direction. So this is going to be X, Y, and then Z is coming out of the page here. For now, just ignore these green lines here. I drew them in advance so that I could have things nicely lined up when we start putting them on the picture. We're going to say that we have, what here, an infinitesimal cube. All right. So this whole thing is infinitesimal in size, which means that the dimensions of it are going to be dx by dy by dz. I didn't draw this perfectly to where I can really write these, but the idea would be that this side over here would have a length on this side of dx. And just to keep the picture from getting too cluttered, I'm only going to draw that on this side, but then this side, because it's in the z direction, would be dz. And then the height of my box right here is going to be dy. That's obviously big, so calling it infinitesimal maybe seems kind of silly, but the idea is that, yeah, dx, dy by dz. And what we're going to calculate here is we want to kind of find the flux of a field out of this cube, or fluid, however you want to think about it. So we're basically going to find the flux. Again, flux is just another word for flow in a way, through the cube. That's our goal. And we can think of flux as basically just being, if we remember, for us, we define flux as being kind of this thing where we do a surface integral of like E dot dA, for example. That was electric flux, right? So really here, what we're going to be looking at is kind of just EDA, just this portion of it, because we're going to go surface by surface here and kind of see what that amounts to. And so to do this, what we're going to say is there's an electric field in this region, and that electric field is going to have different values on different sides of our cube. And what I'm going to use to describe that are going to be these little vectors here. So for example, on the dy's dz plane, we're going to say, for example, that there is the vector field on the left surface. Here, let's draw it like this. I'll draw it like this. It's coming in on the left surface over here, and then it's going out on the other surface over here. And I'm going to call these the x component of the electric field. So this one on the left is going to be the value of the electric field. Here, let's use green for this. This vector on the left right here is going to represent the electric field of the left face of the cube. I'm going to call it E sub x. This over here is going to represent the electric field on the right face of the cube, and I'm going to call that one E sub x prime. They are just different values of the electric field shifted by a distance dx. And then we're going to go in and fill that for the rest of these as well. So we're going to have an electric field that points in the y direction that comes into the top. And we're going to have an electric field in the y direction that comes out the bottom. So the one on the top is going to be EY. The one on the bottom is going to be EY prime. And following up with the last pace, we're going to have the electric field coming in the back and then going out the front. Becomes obvious how horrible my... Here we go, that's more parallel. And these ones are going to be EZ on the back, and then on the front it's going to be EZ prime, because these point along the Z direction. So we've got an electric field in this region. It's called E. It has these components at these locations. Okay, the reason why there's no vector symbols on here is because they're just components, and the components are not... but we have this vector field E in this region of space, and these arrows just represent the value on each of the faces. And what we're going to do is we're going to find the flux through the left face, the right face, the top face, the bottom face, the front face, the back face. There's 6 faces. We're going to add up all those fluxes to get the total flux through the entire object. And we're going to prove that it's related to the divergence of the field. Okay, so that's our first goal here, is we want to prove how divergence is derived from flux, so we can understand kind of what that idea is. And then connect it back to Maxwell's equations. All right, so let's do the EX version first. Okay, so remember that flux is positive when it goes out, it's negative when it comes in, right? So on the left side, let's get if we're gonna start writing this over. So on the left face, the flux is going to be equal to EX multiplied by the area of the left face, which is going to be the same as this one over here, which is dy dz. So that's how we're kind of going to do this. And I'm going to call this one negative because it's coming in. On the right face, the flux is again going to be electric field times the area. So it's going to be EX prime times dy dz. Remember, flux is just electric field times area, right? And then the net flux through those two faces, from right to left, would be the difference between these two. So if we call this like flux left and flux right, then the net flux in that direction, this is the net flux just along the x direction, is going to be basically flux right minus flux left. And so this is going to be equal to E prime minus, sorry, this is EX prime. Because that's the value over here is EX prime. Sorry, it's EX prime. So it's going to be EX prime minus EX, and then multiplied by dy dz. Does that make sense? This is only in the x direction. You'd have 4 other terms. I'm only putting these here because... yeah. Why did they do it all at once? Well, it's a textbook, so they're kind of trying to do everything at the same time. I can do it all at once if you prefer. I think it's going to be a little bit easier to follow if... okay. Yeah, Ash, I could do it. It would really fill up the screen, and I don't think it'd be easy to understand. We will do it all at the same time at the end, but not until we understand like one part of it. Because this one's easy to split up. All right. Okay. So do you all understand this part at least? That the flux kind of flowing in the x direction is going to be this? Okay. All right. So, all right. Now here's the next part of it. This part's a little bit tricky, but it's something that you've kind of seen before. So the next thing to understand is that we can rewrite EX prime in another way. So the idea here is that the electric field is kind of a function of x, y, and z. And if I want to find the value of EX prime, I just really need to know the rate at which the electric field is changing in the x direction. So what I could say is that EX prime is just equal to the value of EX on the left-hand side plus whatever the rate at which the electric field is changing in the x direction multiplied by the distance that we are away. The value of EX prime is just equal to EX plus the rate at which the electric field changes in the x direction. And it's not just the electric field, it's the x component, okay, of the electric field, the way in which that's changing in the x direction, multiplied by the displacement or the change. This equation is no different than the following equation. We'll write it like that because I think it's easy to understand. Does that equation look familiar to you? This is the same equation as, it's one of the first equations you learn about physics. You could learn it as early as like 4th grade, depending on, it's the idea that basically distance equals rate times time, right? Or displacement, delta x is equal to x velocity times time, right? That's what this says, basically. Can you see the similarities? Does that make sense? See, this is just a rate. Del EX, del X is a rate, right? So if I want to find the difference between these two things, I just need to know the rate at which that function changes in the x direction. And if I know the rate at which it's changing and I multiply by the change in x, right, then I get this, which is, again, the same thing as distance equals velocity times time, right? Okay, to continue the rest of the explanation, I'm going to delete this. But that's the idea of what we're saying here, is that EX prime is going to be equal to EX plus del EX del. Okay, now, you can rearrange this to pretty easily see that the quantity that we have up there in parentheses, EX prime minus EX, is really just equal to and what that means is that the kind of net flux in the x direction, we just consider the x components, is now just going to be equal to, well, we replace the parentheses here with the parentheses there, which is this. So you end up getting del EX, del X, the partial derivative of the electric field component in the x direction with respect to x, only the x component, multiplied by dx, dy, dz. Okay? Or, since dx times dy times zz is going to be the volume of our cube here, it's really just del EX, del X times the volume of the cube, dv. And there we go. Kind of a hint at this idea of flux divided by volume showing up. And now what we would do is we would go through and we'd do this exact same thing for all the other faces. But until we do that, do you all understand this part? Anyone have any questions? Okay, so we can go through and play this game on all the faces, basically. We can say, if we do the exact same thing in the y direction, you're going to get basically EY prime minus EY. It's going to be multiplied now by, you got to look at the face there is dx dz, right? So here we put dx dz. And then you basically just, if you can look at the left-hand side of this equation and look at the right-hand side of the equation, you'll notice there's x's at every single point. So if I want to get EY prime minus EY, all I need to do is del EY del Y dy, and then dy times dx times dz, which is also equal to del EY del Y dv. And then the third one you're going to get is going to be del EZ del Z dv. Okay, and then we have to add all of those up. So finally, to get the total flux, what we're going to have is the sum of all of them. So it's going to be del EX del X plus del EY del Y plus del EZ del Z. And that whole thing is times dv, which they all have in common. dv shows up here, here, and here. And then the coefficients are like there. Flux is a scalar, so there's nothing wrong with just adding these all together. There's no more vector symbols in here anymore. But this whole thing right here is divergence. The divergence of the electric field times dv is equal to the flux. So this is why I say divergence is like flux over volume, basically, right? Because now you can write divergence of the electric fields is basically just a way of describing the flux out of a volume. And what kind of a volume? It's the flux out of an infinitesimal volume. That's why you can describe the flux at a point. You can describe the flux per unit volume at a single point by using the divergence here. Now, we can go into more detail later about this, but I might as well at least state right here that we know that the electric flux, the symbol we've used for that in the past, that if we calculate this electric flux over a closed surface of some kind, then we end up getting the charge that's enclosed divided by epsilon naught. All right, this is Gauss's law. But if we're talking about an infinitesimal volume, then the amount of charge that would be contained in such an object, we're going to call dq. That's going to represent the total amount of electric charge that's inside of there, right? And this is flux. So what we can do is, on the right-hand side, instead of flux, we can write dq over dv times 1 over epsilon naught. But dq over dv is the amount of charge contained within the volume divided by the volume, which we often call rho, or the charge density, right? And then what that allows us to do with this equation is just say that the divergence of the electric field is equal to the charge density, rho, divided by epsilon naught. And that would be the first Maxwell equation, Gauss's law. And to complete the story, we can do the exact same thing for the magnetic field, except with magnetic charge density. The magnetic charge density is always 0 because there are no magnetic charges, and so the divergence of the magnetic field is always 0. And this is also Gauss's law, but just for magnetism, right? When you combine these two together, you've got the first and the second Maxwell equations. And these two equations, just like their integral forms, describe all of electrostatics and magnetostatics. These describe static, electric, and magnetic fields and what they do and how they behave. And there we go. It's a pretty good place to stop. Any questions? So now if you see this written on someone's t-shirt, maybe you understand a little bit of what it means. Because divergence is just flux divided by volume, but flux is just charge. And so divergence is flux divided by charge, or charge density. So There we go. That make any sense? I say I just introduced divergence, so you have to kind of go back up and verify, but that is what you have for divergence right there. It's the same thing. Okay, so let's take a break for 10 minutes, and we'll come back and we'll do curl and the other two Maxwell equations. We'll also, if we have enough time, talk about Gauss's theorem and Stokes' theorem. Two things that you probably talked about in your math class, I'm pretty sure.